Two topics will be covered in lecture 13, the boundary conditions, in which part of it has been taught in our class last Tuesday, and the other part will be on the capacitance, which inshallah I'll try to cover it by today. Hopefully we can finish it by today. Yeah, so reference for these two topics can be obtained from the study course. These are the pages, the reference for these topics of boundary conditions and capacitance. Okay, so the objective, there are two objectives as I mentioned last Tuesday. The first one is understood to understand the concept of boundary conditions, and number two, we're going to investigate the fundamental aspects of a capacitance. Okay, so we're going to understand what is capacitance all about. I believe that you have learned about capacitance before in electronics, but going to discuss it further in the field theory, in the field theory, in the view of field theory. Okay, and we are going to calculate the capacitance for any given structure. Okay, so you must be able to fulfill this objective, these two objectives. Right. So the boundary conditions, in our class last Tuesday, we did cover on these boundary conditions between the conductor and free space, and we did these formulations for the case of normal and tangent component for the boundary conditions, and end up we have these two equations, which is for the normal and for the tangent components, and finally we have formulated the equations for the boundary conditions between the conductor and free space. Conductor and free space, if we can base on these slides. For conductor and free space boundary conditions, the equation shall be simply given by rho s over epsilon naught in the normal direction. Means that if you base on this equation, if we have a boundary, if you base on this figure, if we have a boundary between the conductor and the free space, so this is the boundary, that we have between these two medium, it can be noted that the E field will be produced or will exist only on the free space region. Only on the free space region. In which the E field in the free space region shall be given by rho s over epsilon naught in the normal direction. Rho s over epsilon naught normal direction, which means that rho s is the surface charge density on the boundary, on the boundary between the conductor and the free space. And we know that for the conductor, the electric field inside the conductor is equal to 0 all the time, which has been learned in lecture number 10 before. Okay, so just repeat again that if you have a conductor and free space environment or free space boundary, the E field will exist only in the free space region, and the direction of the E field will always normal with respect to the conductor surface. Normal means that the E field will be away from the conductor surface with the magnitude of rho s over epsilon naught. Okay, the same thing is applied if you have a case whereby the free space is now changed with the dielectrics. With the dielectrics, in which we know that the dielectric will be having a permittivity of epsilon, in which epsilon should be equals to epsilon naught multiplied with epsilon r. Epsilon r is relative permittivity, which has been learned in our class in lecture 12 previously. Okay, so for this particular case, if you are having a dielectric to replace the free space, we are going to say that, or we can say that the electric field will also exist only in the dielectric material or dielectric region, in which the E field will be equals to rho s over epsilon in the direction of normal. So we just change the permittivity of free space that we have in the free space with the permittivity of epsilon related to the dielectric material. Okay, so the concept should be the same. We just change the value of permittivity from the epsilon naught for free space to epsilon for the dielectric material. Okay, so that should be the boundary conditions between the conductor and dielectric, which is almost similar with the case of conductor and free space boundary conditions. Right, so I think that you have understand this very well on the conductor and free space boundary conditions. So let's have a look on this first example, yeah, in which we are given here in this example that there is a point on the conductor and free space boundary. The electric field is given to be 2x plus 3y, yeah, to direction of x plus the direction of y, volt per meter. So you need to find the rho s at the point on the boundary, yeah, find rho s at the point on the boundary and d at the boundary, yeah, rho s at the point of the boundary. Okay, so we have learned previously from the previous slide that in this particular case, we are dealing with the conductor and free space, yeah. Okay, so this is your conductor. Okay, conductor material called the medium. This is your free space medium. I just use Fs, which stands for the free space region. And we know that for this particular case, electric field will only exist on the free space region. Yeah, sorry for that. Yeah, only exists on the free space region. So that should be the E field direction, which is normal all the way. Okay. Right. So that E field should be given by rho s divided by epsilon naught in the direction of normal. Yeah. So that should be the E field that will exist for the case of conductor and free space boundary. Okay, and it's given in the question that the E field is provided. So which means that the E field that's given in this problem basically is the E field that exists in the free space, because we have learned previously that when we have a boundary between the conductor and free space, the conductor E field will be zero all the time. Yeah. So the E field that will exist is related to the E field that we have. I mean, it is based on the E field that is provided here. Yeah, which is the E field only in the free space environment, in which we can see that from this relationship between the provided E field and the E field from the formulation, we can see that the rho s over epsilon naught of normal direction okay, shall be equals to 2 of x, okay, plus 3 direction of y. Yeah, rho s over epsilon naught direction of normal should be equals to 2 direction of x plus the direction of y. Yeah, so this is the case now. Right. So what we can do now is that based on the question, you need to find the rho s at the point on the boundary, and afterwards you need to find the vector d at the boundary. Okay. So what we can do is that we can write this vector in terms of the magnitude and unit vector. Yeah, because we want to have a similar form with the left-hand side, yeah, because the left-hand side is a vector which is in the form of magnitude and unit vector. So by right, we need to change the right-hand side form into a magnitude and unit vector form, in which basically this will give us, yeah, 2x plus 3 direction of y. Basically, we can write this as square root, yeah, of 2 squared plus 3 squared, which is the magnitude of this particular vectors. And in the vector for that will be equals to 2 direction of x plus 3 direction of y divided by the magnitude, which is, if we base on this equation, it should be equals to set of 13. Yeah, set of 13. Okay, so basically we can say that this magnitude, yeah, the magnitude of these particular vectors, yeah, should be equals to set of 13. Okay, and the vector for that will be equals to 2 direction of x plus 3 direction of y divided by set of 13. I'm very sorry about this this step problem, I believe. Yeah, I'm not sure what's the problem of this line. Suddenly it's come out. I'm very sorry for that. Yeah, it's very irritating. Okay, this is 2x just now. Okay, so we have set of 13. Yeah, this is 3y. Okay, in which if we base on that, we can say that if we compare the left and the right hand side, we're going to have that the rho s over epsilon naught should be equal to set of 13. Yeah, and which from here we can see that the rho s finally will be equals to set of 13 multiplied with the epsilon naught. So that should be your rho s in the units of coulomb per meter squared. Yeah, so that should be the surface charge densities, which is at the boundary between the conductor and free space. Okay, right, so that should be the first, the rho s at the point on the boundary. And afterwards, you need to find the D, which is the flux density at the boundary. Yeah, so we have learned that at this particular boundary, the only field that exists will be the E field on the free space environment. So from here, we can straight away say that from the equations of D equals to epsilon naught of E, and because we are dealing with the free space environment, so we can say that the D will be equals to epsilon naught multiplied with the E, which is rho s over epsilon naught direction of normal. So simply we're going to have rho s direction of normal straight away. Okay. All right. Or we can also say that, yeah, because we have calculated just now that rho s is 13 over epsilon naught. Yeah, so we can also write this as set of 13 epsilon naught in the direction of normal. Yeah, in the coulombs per meter squared. Okay. Any question for this example number 1? Basically, example number 1 is just to use the equation of the E field, I mean the boundary conditions for the conductor and free space environment. Yeah. Okay. So I won't be doing example number 2, yeah, because the method, the problem is almost similar. It's example number 1. So you can proceed this on your own because there is a yeah, the method is similar. You're going to find the E field, find the rho s. Yeah. So, but if you face any problem with example number 2, please consult me. Yeah, you can just PM me for further discussion. Okay, so let us proceed with the next boundary conditions because we have stated before that 3 boundary conditions will be covered in this chapter number 13. Yeah, if you can base on this previous slide. Yeah, so we're going to see 3 types of boundary conditions in electrostatic. The first one is conductor and free space, which has been covered. We'll also learn about the conductor and dielectric indirectly, yeah, because these two are similar in terms of the E field, whereby the E field will be rho s over epsilon direction of normal. Yeah, the difference will be only on the permittivity value for free space and dielectrics. And we have agreed that this E field will only exist on the free space environment. Yeah, no E field in the conductor region. Okay, so the third one will be on the boundary conditions between dielectric and dielectrics, which we're going to cover it now. Okay. Okay, so this is the one. Okay, so the formulation for these boundary conditions between dielectrics and dielectrics is similar to what we have done previously for the conductor and free space boundary conditions. Yeah, it's almost similar. The difference will be on the material itself for sure. Yeah, because if you base on this diagram, yeah, the first material here is the dielectric number 1, and then we have dielectric number 2. Okay, and we assume that there is a boundary between the dielectrics. Okay, and the boundary is said to have a surface charge density of rho s. Yeah. Okay, so we can see that this particular application of boundary conditions, yeah, if we can have a short discussion on that, we can see that this happened in the case of light propagation in the fiber optics. Yeah, I believe that you have done. I mean, you know what fiber optics is all about. Yeah, I believe that all of you use Unify. Most of you use Unify. So Unify is to be based on broadband, in which fiber optic is the medium of data transmission. Okay, so we have a fiber optics. Okay, fiber optics, the cross section should be look like this. Okay, so the light will be propagating inside this fiber optics material, fiber optic structure. Okay, and for fiber optics, we have 2 regions in which we have the core material is here in the middle, and then we have the cladding. We just call it as a clad. Yeah, so the core, this is the cross section, yeah? The cross section from the side of your fiber optic structure. So the core, let's say, is having a refractive index of N1, and the clad is having a refractive index of N2, in which refractive index N is related to this permittivity from the equations of N of epsilon R mu R. Okay, so epsilon R, you have learned this in dielectrics before. So mu r is for the relative permeability, which will be learned in magnetostatic later on, the part 2 of EMT. Yeah, but this is relationship of the refractive index and the permittivity and permeability value for the material. Okay, so these two materials are dielectrics. Yeah, because for the fiber optics, normally we fabricate it using glass. Yeah, from a glass, silica, and also for the clad, it's also silica. But for the case of light to propagate in a core, the refractive index of N1 should be bigger than N2 to enable the total internal reflection. Yeah, total internal reflection, which is based on the Snell's law. Yeah, I believe that you have learned this in physics. Yeah, the total internal reflection. Yeah, the TIR. Okay, so we can see that there is a boundary, yeah, between the two medium. Here we have the first medium is a core, a glass, and second medium is also glass, but with a lower refractive index. So both of the materials are dielectrics. So we can say that at this particular boundary, there should be a I can say the effect of the boundary conditions between the E field propagating in the core, yeah, and the E field that is said to be, I can say that it is what we call as a accidentally, yeah, accidentally pass through the clad, yeah, because for the case of total internal reflection, the assumption is that all of the light, yeah, all of the light, yeah, will propagate only in the core, but somehow due to the structure of your fiber optics, yeah, due to the bending of fiber optics or due to the I can say a small particles at the boundary between the core and the clads boundary here. So some of the light might accidentally pass through the clad region. Yeah, it can pass through the clad region. Okay, so that should be the effect of boundary conditions. Yeah, because in this particular case, we are having two materials in contact. Yeah, in this particular case, we have a core and a clad, where both of them are dielectric. Yeah, so this is the examples on how we can examine the effect of boundary conditions between two dielectrics region, which are in contact with one another. Yeah. Okay, we come back to this formulation of boundary conditions between dielectrics. Okay, so we have this case of boundary where we have the rho s, the surface charge density, and the boundary between the dielectrics, and this will be the case as we have seen before for the case of conductor and free space, in which again we have to separate both E field into tangent and normal components. Yeah, E1 and E2, both of them. And afterwards, what we have to do is that we have to find a relationship between the E1n and E2n. Yeah, we need to find a relationship between these two E field component, and then we also need to find a relationship between the E1t and the E2t. Yeah, between the tangential component relationship. Okay, so later on we're going to formulate the equations. So that will be the things in which we have seen this before in conductor and free space boundary condition. So I don't have to proceed this anymore. So we just see here that the first boundary condition, which consider the normal components, will be given by epsilon 1. Yeah, based on this will be epsilon 1 of E1n minus epsilon 2 of E2n equals to rho s. Yeah, E1n is a normal electric field in the first medium. E2n is a normal electric field in the second region. Yeah, this will be epsilon 1, which is permittivity in the first dielectrics, and that will be epsilon 2, which is permittivity in the second dielectrics. So this will be relationship between the E1n and E2n, where the rho s is the surface charge density on the surface of the boundary. Yeah, or surface charge density at the boundary of the dielectrics. Okay, so we have done a normal component, and also for the tangent component, this is the things that we have seen also in our class last Tuesday. And for this, we have formulated the equation, which is based on the second law of Maxwell, the closed loop integrations of E dot dl equals to 0, and end up, you can prove this on your own, that E1t equals to E1t. Okay, so this will be the boundary conditions for the tangent component between the E1 and the E2, yeah? Right. So we have two boundary conditions that shall be applied in solving the boundary conditions problem between two dielectrics. The first one is the normal components given by these equations, yeah, number one. And number two is relationship for the tangent component given by this equation number two. Okay, right. So we can then proceed with this example number one, in which we're going to apply the equations that we have formulated in the previous slide. Yeah. Okay. So for the first example here, we are given that in the region of y equals to 0, we find that the relative permittivity for first dielectric is 4, and in the region y less than 0, we find relative permittivity for the second dielectric equals to 3. If E1 equals to 10 of Z at the boundary, find the following parameters. Yeah. Okay, so the assumption made here is that rho s equal to 0 at the boundary. Okay, let us sketch the problems. So basically, the boundary of these dielectrics should be given by y equals to 0. Because it's mentioned in the problems that for y bigger than 0, yeah, we have the first dielectric material where relative permittivity is equals to 4 given here in the statement. And for the second region, whereby y less than 0, this will be for the second dielectrics in which the relative permittivity equals to 3. Okay, yeah? And it was given that the E1, which is the electric field at the boundary, but at the medium number 1, yeah, E1 is for medium number 1, yeah, is equals to 10 of Z. So I can say that the E1, which is electric field at the boundary, but at medium 1, equals to 10 direction of Z volt per meter. Okay then, yeah, so from this diagram that we have sketched based on the given statement, you need to find what should be the flux density in medium number 1. Yeah, so that's the first question. Let us proceed with the first question. So I think for the first question, it won't create much problems because we are given the E1 already. So the D1 should be based on the equations of epsilon naught, epsilon R1 multiplied with the E1, yeah, in which we are going to have it as equals to 4 epsilon naught multiplied with the E1, which is 10 direction of Z, and that will give us 40 epsilon naught direction of Z in coulombs per meter squared. Okay, so that should be our flux density in medium number 1, which is at the boundary. At the boundary. Okay then, yeah, just a straightforward question, should be no problem at all. Okay, number 2, we need to find the E2, which is the electric field in medium number 2. In this particular medium, we need to find what is the electric field value. Okay, so this is where we need to apply the boundary conditions, equations that have been formulated before, in which we have number 1, the equation is epsilon 1 of E1n minus epsilon 2 of E2n equals to S. And the second equation, which is for the tangent component, is E1t equals to E2t. Okay, so that should be the equations to be used in this particular problem to find the electric field at another region. So which means that the boundary conditions equation can be used if you are given the E field at one region and you need to find electric field at another region. So this is where you need to you can use the boundary conditions equation to find this electric field values. Yeah. Okay. So for this, if you want to use this equation, first of all, what you have to do is that you need to separate, or you need to find what is the E1n, because from the first equation here, yeah, from the first equation, because you have been given the assumption that rho s equals to 0, so this equation can be further simplified to be epsilon 1 of E1n shall be equals to epsilon 2 of E2n. Yeah, because rho s equal to 0, yeah? So from this equation number 1 here, if E1n is known, so you can simply find the E2n, am I right? Yeah, because the E2n shall be equals to epsilon 1 divided by epsilon 2 multiplied with the E1n. Okay, so if we know the E1n, so you must be able to find the E2n. Okay, similarly, for the second boundary conditions, if you know the E1t, you must then able to find the E2t. Yeah, so you can find the E2t straight away from the equations of, yeah, straight away from the boundary conditions that have been provided, whereby the E2t equals to the E1t. Okay, so that should be the second boundary conditions to be used. So from here you have the E2n, you have the E2t, and from this E2n and E2t you can find the E2. So that's the idea. Yeah, so that's the idea of having this boundary conditions equation. Okay, so the things that you have to do now is that you have to obtain what is the E1n, what's the E1t, so that you can find the E2n and E2t respectively. Yeah. Okay, so for this, you are given the E1, and you need to know what should be the direction of normal linear vector with respect to this boundary of y equal to 0. Okay, so from this, we know that the normal linear vector shall be equals to y direction. Yeah, normal linear vector should be equals to y direction. Yeah, so you can prove this on your own that normal will be y direction. And from here, from this uh, uh, characterization, or knowing that the normal is y direction, so we can find that the E1n will be equals to the E1 vector dot product with normal linear vector. Yeah, that's how we define the E1n, yeah, because E1n shall be calculated based on the dot product between the vector E1 itself and the normal linear vector. And from here, we can say that since E1 equals to tan of z, and normal is direction of y, so your E1 value shall be equals to 0. Yeah, so E1 equal to 0, which means that from this calculation of E1 equal to 0, we can say that the E2n will also equals to 0. Okay, the E2n will also equal to 0 because our understanding from the first boundary conditions here state that if E1n is 0, so E2n straight away will be 0. Yeah. Okay. So from the equations, we know that the E1 basically is written to be a combination of E1n vector plus E1t vector. Yeah. So this is the we know this relationship. Yeah. Normal and tangent summation of this will provide the E1. So knowing that E1n is 0 from our calculation just now, we can say that the E1t will be equals to the E1. So which means that this particular E1 vector basically is your E1t. So from this mathematics equation, yeah, from this equation, we can say that the E1t shall be equals to tan direction of z, and this shall be equals to E2t vector. That is from this boundary conditions number 2, which states that the E2t equals to E1t. Okay, please take note that this boundary condition is in terms of magnitude, yeah? It's not a vector. E2n magnitude equals to this permittivity 1 divided by permittivity 2, E1n magnitude. The same things applied for E2t magnitude equals to E1t magnitude. But we can simply change this into a vector. We just vectorize this equation. Supposedly, that should give us E2t vector equals to E1t vector, yeah, straight away. So from here, we can say that the E1t equals to E2t, which is tan direction of z. And if we combine this value, the E2n is 0 and E2t is equals to tan of z. So E2 magnet vector will be equals to E2n vector plus E2t vector. And knowing that this is 0, so end up we're going to have that the E2 will be equals to tan direction of z also. Okay, so that should be our E2 obtained from the use of boundary conditions.
Doctor.
Yes.
Why the normal is the direction y just now for the dielectric one?
Oh, okay. if we base on, okay, this is Z, this is X, and this is Y. Okay, Wehan, can you please help me? Where is the plane of Y equal to 0?
SY plane.
Correct. That should be the one, right? Exact plane. Am I right? Y equal to 0 should be that one.
Yes, yes, yes.
Yeah, so the normal should be in this direction, right? Which is Y direction. Am I right?
Oh, okay, okay, okay.
Okay, good. Thank you
And
very much. Yeah. Okay. Hopefully, this will help others also to understand. Thank you, Johan, for the question. Okay. I hope all of you understand the selection of this unit vector. Yeah. So I shall erase this. Or can I erase all of this? Yeah. Sorry for this. Yeah, because I don't have time to erase one by one. Okay. Thank you for that. Okay. So for number 2, it is a D2. Okay. So that should be based on the first E2 that obtained previously. So D2 can be calculated. Yeah, so D2 can be calculated based on the equations of D2 equals to E epsilon 2 multiplied with the E2 vector. So we have been given that the epsilon R2 is 3, so we can say that that should be equals to 3 epsilon naught multiplied with 10 of Z, and we're going to have it as 30 epsilon naught direction of Z, yeah, in coulombs per meter square unit. Okay, so that should be the D2, yeah. Okay, and next is to find the P1 and P2. So that should be based on the equations that we have seen in our class last Tuesday, where we have learned that D vector equals to epsilon naught of E field plus the vector of P. And from this, we can find that the P vector shall be equals to D vector minus epsilon naught of E field. Yeah, for instance, if you want to find the P1, yeah, which is for the first medium, dielectric number 1. So P1 shall be equals to D1 vector minus epsilon naught of E1 vector. Okay, so we can have this as D1 just now is equals to 40, okay, epsilon naught of E1, yeah, minus, sorry, E1 minus, sorry, not 40, is 4, I apologize, yeah, it's 4, sorry for that, it's my mistake, it will be 4, okay, minus epsilon naught of E1, and that will give us 3 epsilon naught of E1, or equals to 30 epsilon naught direction of Z in coulombs per meter square unit, yeah, that's unit for the P1, and the same thing is applied for the P2, yeah, for the P2, where we have for medium number 2, the P2 vector should be equals to D2 minus epsilon naught of E2, okay, and that will give us 3 epsilon naught of E2 minus epsilon naught of E2, and that will give us 2 epsilon naught of E2, okay, and subsequently we can have it as equals to 20 epsilon naught direction of Z, yeah, coulombs per meter square, because both E1 and E2 are having same value and same direction. So we have this P2 value, yeah. Yeah, so P1 and P2 has been calculated based on this method, yeah. Okay, for the rho SB, for F part F is to find the rho SB. So rho SB is a surface bounded charge densities, which has been learned in our class last Tuesday. So basically, if we have a boundary, remember the boundary that we have here, first material, second material, yeah, we have the first dielectric, this is 4 epsilon naught based on this value, and the second one is 3 epsilon naught. Okay, so because we have a dielectrics in contact, so basically there should be a surface bounded charge rho SB, which will be formed at this particular surface. Yeah, this is a surface bounded charge. Yeah, so I can label this as rho SB1 because this surface bounded charge is related to the first dielectrics. And also we can have rho SB number 2, which is labeled down here. Yeah, so please view it clearly, carefully here, that The black dotted here, which is for the rho SB1, is related to first dielectrics, whereas for the second rho SB, which is rho SB2 here, is basically the surface bounded charge for the second dielectrics. Yeah, because we have learned that the surface bounded charge is not a free charge, but it's a surface charge which is bounded to the atom. Yeah, bounded to the atom. So that's why we have these two surface bounded charge with respect to different dielectric material. Okay, so based on this, we can say that the total rho SB, yeah, total rho SB shall be equals to rho SB1 plus rho SB number 2. Yeah, we need to add them together, which is at the boundary. So we have learned that rho SB1 is based on the equation of P dot N, yeah, P dot N, and since rho SB1 is related to the first dielectric, so you have to use the vector P for first dielectrics, yeah, P dot 1. So I need to erase this. Okay, so that should be P dot N, yeah, P1 dot N. Okay, that should be for the rho SB1 plus for rho SB2, it should be P2 dot N. Yeah, sorry, P2, not a linear vector, it's a vector, yeah. So P2 dot N, yeah, P2 is for medium number 2, which is the vector of polarization for second dielectrics, in which both of these P1 and P2 has been calculated from D and E part respectively, yeah. Okay, so from here I believe that you can try to solve this on your own. Okay, but you have to be very careful on the selection of normal linear vector. Yeah, for instance, if you base on the first dielectrics, which is to find the rho SB1, yeah, so P1 shall be equals to 30 of epsilon naught direction of Z. But for normal linear vector, you have to be very careful that normal linear vector with respect to this medium should be directed downwards. That should be for the first dielectric, yeah, because you have to remember that normal linear vector for that particular dielectric should be away from dielectric. So based on that, for the first P1 dot N, normal linear vector should be negative Z direction. So negative Y direction, sorry for that, negative Y direction, yeah, negative Y direction. And for the P2, where we have 20 epsilon naught direction of Z, which is for the second dielectrics, yeah, normal linear vector should be directed upwards, and in this case, it should be positive Y direction. Okay, so accidentally, in this particular example, the value of rho SB is 0. Yeah, because Z dot Y and also Z dot negative Y, both of them will give us 0. So it means that for this particular case, there is no surface bounded charge at the boundary. Okay then? Okay, so hopefully you understand this clearly on the first example related to the boundary conditions. Yeah. Okay, I won't be doing this example number 2 because it is similar to what we have done before. Okay, you can try this on your own. If you have any problems, please discuss with me through Telegram channel. Yeah. Okay, I shall proceed now with example number 3. Again, this is on the boundary conditions between the dielectrics. But I'm not going to solve this in full, yeah, because the idea, I think you have the ideas already in solving the boundary conditions problem. But if we base on these particular examples here, we are given that there are two regions, yeah, two regions. The first region is 4x plus 3y bigger than 10, which consists of a dielectric material with permittivity epsilon 1. And then we have a region of 4x plus 3y less than 10, in which for this particular region, it consists dielectrics with permittivity of epsilon 2. So if we can sketch this diagram, we can see that that should be the first dielectrics, the second dielectrics, the permittivity is epsilon 1, yeah, epsilon 1, and the permittivity is epsilon 2. Okay, yeah, and the boundary equation, if you base on this, yeah, this region here is 4x plus 3y bigger than 10. Whereas for this second region down here, the region is 4x plus 3y less than 10. Yeah, plus 3y. Yeah, sorry for my handwriting. It's to be 3y. Okay, sorry. The equation. Yeah, sorry. The equation. Okay. Okay, means that at this particular boundary, the equation for the boundary should be 4x plus 3y equals to 10. Yeah, that should be the boundary equations between the first dielectric and the second dielectrics. Okay, all right. So we are given that E1, which is the electric field at the boundary, and because we have a subscript of 1 here, means that the E field here is related to the first dielectrics. Yeah? So I can just put that we have the E1 at the boundary between the two dielectrics, yeah, which is given by 2 direction of X minus 7 direction of Y plus 5 direction of Z. Okay, plus 5 direction of Z, volt per meter. Okay, so this will be the case. Yeah. So for the first question, which is to find the D1, okay, before that we have to we can assume that rho s equal to 0 at the boundary. So assumption is made is rho s equal to 0 at the boundary. So which made our equations to be easier then, in which if we base on the boundary conditions equation, epsilon 1 of E1n minus epsilon 2 of E2n shall be equals to rho s, and since rho s equal to 0, this has been simplified to be epsilon 1 of E1n equals to epsilon 2 of E2n. Okay, so we have simplified the equation, so it makes our life easier then. And then for the second boundary conditions, we have the E1t equals to the E2t. Yeah, so this is the boundary conditions equations that have been formulated based on the given conditions of these questions. Yeah. Okay, so for the D1, which is the flux density in medium number 1, so straightforward, in which for the first dielectrics, it should be D1 vector, should be epsilon 1 of E1. So that will give us straight away, because that we're not given any value, we are just given the symbol, yeah, of epsilon 1. So it is understood to be a permittivity of the material. So we have epsilon 1 multiplied by the E1, which is given here to X, yeah, minus 7 of Y plus 5 direction of Z. So that should be our D1 vector, yeah, D1 vector. Okay. Is there any questions for this example? No, yeah? Okay, for number 2 is to find the P1. So it's a straightforward. P1, if we base on the equation that we have formulated before, it should be D1 minus epsilon naught of E1 vector. So we're going to have this as epsilon 1 minus epsilon naught, yeah, multiplied with the E field straight away, yeah? Okay, because from here it can be said that epsilon 1 basically should be equals to epsilon naught multiplied with relative permittivity of medium 1. Okay, so it should be looked like this, yeah? So when we say permittivity straight away, it means that this epsilon 1 is equals to epsilon naught multiplied with relative permittivity of that dielectrics. Yeah, so please don't get confused with this. Unless if it's mentioned here, material with relative permittivity. So when it said relative permittivity, so that is epsilon R of the material. Yeah. Okay. Hopefully it's clear on the first and second example. Okay, for a second question, which is to find the D2. Yes, to find the D2. This is basically is to find the E2 first. Yeah, need to find the E2 first. So once you find the E2, then only you can find the D2. Yeah, because D2 simply will be epsilon minus multiplied with the E2. Okay, so to find the E2, this is where we need to apply these boundary conditions. Okay, in which we need, in order for us to use the boundary condition, okay, the E2 can be calculated if we know the E2n vector and we know the E2t vector, in which the E2 basically will be E2n plus the E2t, right? Okay, the E2n can be obtained from the first boundary condition, yeah, that we have that E2n, based on these boundary conditions, yeah, that we have here, based on this, the E2n shall be equals to epsilon 1 divided by epsilon 2 multiplied with E1n. And for the E2, E2t, it should be based on the equations of the second boundary conditions, where we have that E2t shall be equals to the E1t. Okay, so that should be the basis to calculate or to obtain the E2n vector and E2t vector, yeah? Okay, so how to find the E1n then? So that's the first question, how to find the E1, yeah? Okay, so the E1n can be obtained, yeah, similar to what we have obtained before, where the E1n will be equals to the E1 vector dot product with normal unit vector. The E1 is given by this 2x minus 7y plus 5 of z, yeah, so we have it should be 2x minus 7 of y plus 5 direction of z. That should be your E1 vector. And what is your normal unit vector? Okay, so you are given the surface equation, yeah, for x plus 3y equals to 10. So from this equation of the surface, you can straight away find normal unit vector, in which normal unit vector with respect to this surface equation should be 4 direction of x plus 3 direction of y divided by magnitude of the vector, which is 16 plus 9, and that will give us 4x plus 3 direction of y divided by 5. So that should be the normal unit vector. Yeah, so that I can label this as normal unit vector for that particular surface. Yeah. Okay, so what you have to do now is that we have to dot product with the normal unit vector. So it should be 4 of x divided by 5 direction plus 3 divided by 5 direction of y. So it's a dot product between the E1 and the n in normal unit vector, and end up we're going to have this as, when we dot product it, we're going to have 8 over 5, yeah, and that will give us negative 21 over 5. That will give us negative 13 over 5 magnitude. Okay, and from here we can just substitute the E1 into this equation, E1n into this equation. So we're going to have this as epsilon 1 over epsilon 2, and the E1n will be equals to negative 13 divided by 5. Okay, but what we have here is only a magnitude. What we have to do now is that we have to vectorize this equation, yeah, in which what we have to do is that we have to say that from this equation, we can find the E to n vector simply, yeah, simply by just multiply, by just multiply the right hand side with normal unit vector. So we have epsilon 1 over epsilon 2, negative 13 divided by 5 and multiply with normal unit vector, which has been obtained before, which is 4 over 5 direction of x plus 3 over 5 direction of y. So that will give us the E to n vector. Okay. Any question up to now?
Doctor, why the
Yeah.
E2n, the normal vector is same with the E1n one?
Okay, because in this particular case, remember how we formulated equation before? Okay, remember this formulation of equation, right? Normal unit vector is similar for both material, right? The direction is upward.
Oh, okay.
Okay, yeah? All right, thank you. Okay then, so E to n has been obtained based on this method. And from here, I believe that you can find the E1t straight away. Yeah, E1t straight away. Because we know that from the equations that we are given here, that allow me to use this part here, yeah. Okay, we are given from the E1, yeah, the E1 basically composed of E1n vector and the E1t vector. Okay, E1n, I believe you can obtain it straight away, yeah, because we have calculated just now the E1n from here. It should be equal to negative 13 over 5. Okay, E1n is 13 over 5. So from here we can see that the E1n vector shall be equals to the E1n magnitude, which is negative 13 divided by 5, multiply with normal unit vector, which is 4 direction of x direction, 4 over 5 direction of x, plus 3 over 5 direction of y. Yeah? So that will give us negative 52 over 25 of x, okay, of x, minus 3 times negative 13 will be negative sorry for this, yeah, negative 39/25 direction of force. Okay, sorry for this disturbance, yeah, very sorry for that. Okay, so that should be your E1N. Yeah, that should be your E1N. So from this E1N, you can obtain the E1T, okay, because we know that the E1T vector shall be equals to E1 vector minus E1N vector. Okay, so since E1 is known, E1N has been calculated before, so from here you can find the E1T vector. Okay, so from E1T vector that you have obtained here, you can straight away use the second boundary conditions that the E1T equals to E2T. So the answer that you obtain basically shall be equals to the E2T. Yeah, shall be equals to the E2T vector. So from here, from this part, you manage to find the E2T vector, and from the bottom part here, you manage to find the E2N vector, and that will then provide us with the value of E2, which is a summation of E2N vector and E2T vector. Okay then? Okay, so that's how we use the boundary conditions equation to find the E field at another region. Okay?
When we say about E1 equals to E2, we are talking about only the magnitude, or even the vector is also the same.
Okay, if we refer to this, if we refer to this diagram, right, we say that the E1T equals to the E2T magnitude, yeah, because we know that from this diagram, the tangent for both are the same, yeah, which means that the tangential direction for both should be the same, right? Okay, right, so which means that from this equation, initially it is meant for the magnitude, yeah, but if we base on this formulation for both boundary conditions of normal and tangent component, we can see that from this diagram that the tangent direction for both material, I mean for both medium 1 and medium 2 should be the same. Okay? Right. Thank you for the question. Very good. Okay then, I think we have done with this D2. So we have find the E2. So from the E2, I believe that you can find the D2, the flood density D2, and subsequently you can find the P2, which is the vector of polarization in medium number 2. And afterwards, you can find the rho SB, in which the method is similar to what we have done in the previous example. Yeah. So I believe that you can solve this on your own. Okay. So example number 4, I'm not going to do this. You can try this on your own. But if you base on this example number 4, we have another parameters here, which is called as kappa. Kappa. This is what we call as kappa. Yeah, kappa basically is related to the permittivity by the equations of vector P shall be equals to epsilon naught of kappa E of E field. Okay, so that should be a relationship, yeah, between the P and also the E field based on kappa. And if you base on this, you can say that the D shall be equals to epsilon naught 1 plus kappa of E field. So that should be your relative permittivity, which means that epsilon R shall be equals to 1 plus kappa. Okay, so that should be the relationship between the relative permittivity and the kappa directly. Okay then, so I'm not going to do this. You can try to solve this on your own because the method of solving it should be the same with the one we have done previously. Yeah, so try to solve this on your own. Again, if you have any problems with the solutions, then you can discuss with me using the Telegram channel. Yeah. Okay then, that's done with the boundary conditions. So I shall now proceed with the capacitance topic. Okay, so capacitance basically is a device used to store the electric energy. Yeah, I believe that you have learned this in electronics. Yeah, so you have learned that what is the purpose, what is the function of capacitance. So capacitance is to store the energy, the electric energy in the form of charge. Okay, so the capacitance basically is constructed, yeah, using two different materials, yeah, which are the conductors and also the dielectrics. Am I right? Yeah, so the capacitance is made of, I mean, the basic structure of the capacitor should be two plates, yeah, two plates, and also there should be a dielectrics in between the plates, yeah, between the plates. So the plates basically, or normally is made up of conductor material, yeah, the plate is made up of conductor material, whereas the medium between the plates is made up of dielectrics. So both medium, I mean both material, the conductors and the dielectrics, we have learned this in the previous lectures, yeah. So we're going to apply the knowledge for the conductors and dielectrics in understanding further on the capacitance topic, yeah. Okay, so if we base on this diagram, yeah, so if we enlarge the capacitor structure, yeah, so the capacitor, as I mentioned before, is made up of two plates here. So we have two plates in which one of it should be having a positive surface charge, yeah, positive surface charge, and another one should be a negative surface charge. It's understood, yeah. And we know that the conductor, the charge will only exist on the surface of the conductor. That is why in the conductor we are only having a surface charge density, yeah, a surface charge density then, yeah. Okay, and the placement, the location of the positive surface charge and negative surface charge will be determined by the direction, I mean by the potential difference direction, yeah. So in this particular case, because the VAB, the positive terminal is connected to the positive, to the conductor A, and negative terminal is connected to the conductor B, so that is why the E field should be then directed from conductor A to conductor B, yeah, based on this polarity of your conductor A and conductor B. Okay, and in between these two conductors, we are having dielectrics of the permittivity epsilon. Okay, and we know that as I mentioned before, the charge on the conductors, both conductors A and B, will only will only exist on the surface of the conductors. So that we can say that based on this, the charge amount on conductor A can be written as integration of rho s ds straight away, yeah, and also on conductor B, because it is a negative charge, the charge will be also integration of rho s ds, but having a negative polarity. Okay, yeah. Right, and from this equation, I mean from this diagram, we know that this is what we have learned in electronics, where the capacitance C shall be based on ratio between the charge amount and also the potential difference between the plates. Yeah, VAB is a potential difference between conductor A and conductor B, or in other words, VAB is potential difference between the plates of your capacitor. Okay, Q here is a magnitude, yeah, it's a magnitude at either one of your conductors or either one of the plates. Yeah, so Q is not a summation of the charge in conductor A and conductor B, but indeed Q is a charge amount at whether it's in conductor A or in conductor B only. Yeah, so for this we can write that the Q shall be written as integration of rho s ds. Yeah, because we just deal with the magnitude of the charge. Yeah, the charge, right? And the VAB, we can write this because we have learned about the potential difference in chapter 4, and we know that the direction of your E field is from conductor A to conductor B. So we can write that the VAB will be written as negative integrations of E dot dl. Yeah, this is the E field. Yeah, that's the E field. Yeah, and due to the direction of the E field from A to B, your integration will be the other way around, which will be from B to A. Okay, so this is basically the equation that shall be used in calculating the capacitance for any given capacitor structure. Yeah, so if you understand this concept clearly, so you must be able to find the capacitance for any capacitor structure. Yeah, okay. So this is what I mentioned just now regarding the capacitance equation. So we can use either equation number 1 or you can use other equation number 2. Yeah, but most of the time we can apply equation number 1. So from where we can find, I mean from where we can find this relationship between the rho s and epsilon E. So this is to be based on the boundary conditions. If I can based on this diagram here, this is your conductor plate or the positive plate of your conductor. This is your dielectrics, yeah, dielectrics. I label this as dielectrics. So yeah, and this is a conductor, which is the positive plate of the conductor. So we know that when we have this condition between the positive and the negative, positive conductor, positive charge of conductors, and dielectrics, the boundary conditions will exist between conductor and dielectrics, in which the E field will exist only here. Yeah, will exist only in the dielectric material, in which the E field is normal with regard to the conductor surface, and the E field will be given by rho s over epsilon direction of normal, if you assume that the charge density on the surface of conductor is rho s. Yeah, so we have this is the E field. Okay, and from this equation we can see that the rho s, which is the charge density on the surface, shall be written as epsilon E dot n. Yeah, epsilon E dot n. So that should give us the rho s. And if we substitute this into the equations here, yeah, we're going to have initially from equation rho s ds. So that should give us epsilon E dot n and multiply with the ds. So end up we're going to have integration of epsilon E dot ds. So that's why we have this equation. Yeah. Okay, just a matter of formulating the relationship between equation number 1 and equation number 2. But don't worry on this. If you understand equation number 1, you can straight away use equation number 1 only. Yeah, you don't have to worry. Yeah, you don't have to worry about equation number 2. But the purpose of portraying this proving is for you to understand further on what we have discussed before. Yeah, so what we have discussed before is very crucial, because the understanding will be used again and again, because that is a concept. Yeah, the conceptual thing is very important in EMT. Okay then. So so for the rest of this capacitance topic, we are going to apply only equation number 1 to find the capacitance for the capacitor structure. Yeah. Okay, so let's have a look at this example number 1. We are given a capacitance of we are given two concentric metallic spheres which are separated by a dielectric with permittivity epsilon. Let RB be the inner radius of the outer sphere and RA be the outer radius of the inner sphere. Okay, so if I can sketch this diagram for you, we are having a sphere. Yeah, we're having two spheres. Okay, we're having two spheres. Right, in which the inner sphere is having a radius of RA, I believe. Yeah, based on this, RA the outer radius of the inner sphere, and then we have for the outer sphere is having the radius of RB. That should be the case, yeah, based on these informations given, inner radius of the sphere. Okay. So we have sketched. Yeah, we have sketched these problems based on the given information. And provided that in between the sphere, there's a dielectrics of permittivity epsilon. Okay, so this particular structure where we have two conductors, and in between there is a dielectric which is sandwiched, yeah, sandwiched between these conductors. So we can see that this is a capacitor structure. Yeah, this is a capacitor structure which is in a form of sphere. Yeah, it's a form. So in other words, we can say that this is a spherical capacitor. Yeah, a spherical capacitor. Okay. So for this particular case, the question asks us to find the capacitance of this structure. Okay. So to find the capacitance, you have to go back to the basic equation where we have Q equals to integration of rho s ds divided by integrations of E dot dl negative okay, negative E dot dl, the equations to find the capacitor. Sorry, not the Q, I apologize, my mistake. Not the Q, sorry for that. It should be C, yeah, capacitance. Yeah, capacitance is given by this equation. Okay, so in this particular case, what we can do, because we are not given any information of the rho s, you're not giving any information about the E field, so you have to do assumption in solving this problem, in which in solving the capacitor problem, you need to assume where is the location of your surface charge density. So we assume that the inner sphere is having a positive surface charge density. Okay, so we call this as a positive rho s. So I label this as a positive rho s surface charge density. And outside here, which is at radius of RB, so this is the position of your negative rho s charge. Okay, so this is your assumption that need to be done. Yeah, the position of your surface charge density, the positive and negative. Yeah, it doesn't matter. You can also put positive outside and negative inside with no problems. Yeah, because that will only change the direction of the E field. Yeah, but the method of solving should be the same. Because if you put the rho s in this particular position, yeah, remember, yeah, because if I base on this, the inner sphere here is a conductor, yeah, so the charge will only exist only on this conductor of RA. The same things apply. The charge will only exist on the surface of conductor RB. Okay, so if we have the positive rho s at RA and negative rho s at RB, so your electric field will be directed from RA to RB. So that should be the direction of the E field. If you base on this position of your surface charge, positive and negative. But if you twist or you change the direction of, if you change the position of your charge, in which you change positive to be located outside and negative to be located inside, then the E field direction will be changed also. Okay, so that's why I mentioned this now. It doesn't matter where is the location of your surface charge, as long as you identify one of the plates should be positive and one of the plates should be negative. Yeah. Okay, so based on this, we know that the rho s has been identified, but you need to obtain the E field now. So how to find the E field? So to find the E field, because this is based on a spherical structure, you can use the method of Gauss Law to find the E field. Yeah, to find the E field, in which we have learned in chapter 3 that the D dot ds shall be equal to enclosed charge, yeah, in which we are using the Gaussian surface. Yeah. Yeah, because remember, yeah, this is this E dot dl basically is the VAB. VAB, which is the potential difference between conductors. Yeah, potential difference between conductors, which means that your E field basically should be the E field in between the two conductors. So you have to remember this. Yeah, I repeat again. Since VAB here is the potential difference between the conductor RA and conductor RB, so your E field that you want to use here should be the E field that is located, that is exists between radius of RA and radius of RB. So that is why we find the E field between the RA and between the RB. So our interest will be here in this region, R between RA and RB. Yeah, so that should be our interest then. So from here we can see that left hand side will give us dr of 4 pi r squared, and the enclosed charge, which is the charge enclosed by the Gaussian, that will give us rho s. Okay, so it will give us rho s of 4 pi of RA squared. Yeah. Okay, and then we're going to have a dr that will be equals to rho s RA squared divided by R squared, and subsequently we're going to say that from here the vector D shall be equals to rho s RA squared divided by R. Sorry for this interruption. Okay, R squared here, sorry for that. And subsequently from here we can say that the E field, yeah, between RA and RB shall be written as rho s RA squared divided by epsilon of R squared. So that should be the E field that we shall use now. Okay, so we're going to substitute this E field. Okay, we're going to substitute this E field in this equation of C. So then we're going to have equals to, okay, so for this integration of rho s ds, we just choose one of the plates. So in this case, we choose the plate at RA radius. So we're going to have rho s multiplied with 4 pi RA squared. That should be the area for that spherical surface. And for the negative E dot dl, we're going to have negative integration Okay, negative integrations of E, which is rho s RA squared divided by epsilon R squared, direction of R, and dl, we just choose a positive value, which is the other direction of R. And your integration, since the E field directed from RA to RB, so your integration will be the other way around, which must be from RB to RA. Yeah? Okay, so we solve for the integration. I brought it here. So your capacitance C shall be rho s 4 pi RA squared divided by rho s RA squared. Okay, and down here we're going to have going to have 1 over R. Yeah, 1 over R. Okay, 1 over R, and that should be equals to, let me see, so we're going to have 1 over R squared, 1 over R squared dr, so that we should give us 1 over R, so that should be from RB to RA, yeah, RB to RA, and that can be cancelled out in terms of the RA, right, and OS can be also cancelled out, so we're going to have 4 pi, okay, divided by 1 over RA minus 1 over RB. Okay, so that should be your capacitance in farad. Okay then, any question? So if you base on this equation of capacitance, it can be said that the capacitance for this particular structure should be determined by the radius of both conductors, yeah, which means that because based on these equations, yeah, the RA and RB will be the main factors that determine the capacitance value. So basically, this will help you in designing the capacitor, the capacitance according to your design. Yeah, because from this equation, you understand what are the factors that will influence the capacitance value. Okay, so that's the beauty, the importance of learning EMT, because you are learning something from the basic. Yeah, because in electronics, you learn it just on the surface, right? But here in EMT, you're learning from the basic equations, how to formulate the capacitance equation, and what are the factors that really influence the capacitance value. Okay, interesting, right, EMT? Okay, so that should be the capacitance for this given capacitor structure. Okay, we shall now proceed with this example number 2, in which we are having the same structure, I mean not same structure, the same problems, but having a different capacitor structure. Yeah, for now the capacitor is in terms of coaxial capacitor. Yeah, coaxial capacitor in terms of cylindrical structure. Okay, capacitor in which we are having two conductors having radius of RA and radius of RB, and in between there is a dielectric. Yeah, so we can say that this is the capacitor because we have two plates of conductors and in between there is a dielectric. So this is we can classify this as a capacitor. Yeah. Okay, so use the capacitance equation. Yeah, where we have C equals to integration of rho s ds divided by negative integrations of E dot dl straight away. Okay, so we choose that the rho s should be located inside, where positive rho s, and negative rho s is located outside. Yeah, so this is our assumption, the location of your charge density, positive and negative. So we assume that the positive is at the RA and negative surface charge is at RB. So from this assumption, we can say that the electric field will be directed outwardly. So that should be the direction of the E field based on the assumption of your rho s positions. Yeah, so that should be the E field. Yeah, in your dielectric region. Okay, so our concern is to find the E field between the region of RA and the region of RB. So this is your interest. Yeah, the region of interest, because you want to find the E field to be used in finding this capacitance value. So to find the E field, we need to apply the Gauss Law. Okay, so we have a d dot ds equal to the enclosed charge. So I don't think I have to sketch the Gaussian surface for you again, because most of you have understand this clearly, in which we can see this from your test 1 before. Most of you get good results for test 1 due to your understanding, I believe. Yeah. So we have for this, we're going to have dr, and the ds will be written as 2 pi r of L, whereas the enclosed charge will be rho s, and that will give us 2 pi Ra of L, yeah? So this can be cancelled out, yeah? 2 pi and L can be cancelled out, left only the dr of rho s of Ra divided by R only. And from here, we can straight away say that the E field in your dielectric should be equals to rho s Ra over epsilon of R direction of R, yeah? That should be the E field. Okay, so we're going to use this in this equation to find the capacitance. So we're going to have integrations of rho s ds. So we can straight away find the capacitance, the charge amount, if we choose the charge on the surface of Ra. So that will give us rho s of 2 pi RAL. If we assume that the length is L, okay, and then we divide it with this negative integration of E dot dl. So negative integration of E, which is rho s of Ra over epsilon R direction of R dot dr direction of R. Yeah, that should be E dot dl. Yeah, and since the E field is directed from Ra to Rb, so your integration will be from Rb to Ra. Yeah. Okay, so we're going to have rho s of 2 pi RAL divided by, this is positive. Okay, so we are going to have rho s, Ra is taken out over epsilon, and that will give us ln of Rb divided by Ra, yeah? So we can cancel out few items here. Rho s can be cancelled out, Ra can be cancelled out. So left only with 2 pi epsilon L divided by ln Rb over Ra. Okay, so that should be a capacitance value. Right, so again, if we base on this value for the capacitance, we can see that the capacitance value for the coaxial capacitor type shall be depending on the L, the length of capacitor, and also the radius of the plates, yeah, Ra and Rb. Okay, so that should be the capacitance in farad. Okay then, any question for example 2? No? Okay, if there's no questions, I think for example 2 or 3, I think you can try to solve this on your own. Yeah, try to solve example 3 and example 4 and also example 5 on your own. Yeah, so 3 examples. I left this for you to solve this on your own. Yeah, hopefully you can try this on yourself. So if you face any problem with this solution, you can always, I'm free to discuss these issues. Yeah. Okay, so that should be the end of chapter 5. So chapter 5 quite a long chapters. Yeah, in which in short we can say that we have learned a lot on the material, specifically on the conductors and also dielectrics. Yeah, in which from here we also learn about the resistance, we learn about the boundary conditions, and also we learn about the capacitance. But remember that the first thing that we have learned in chapter 5 is about current. Yeah, current. Yeah, so current is the things that we have learned initially in chapter 5, which will be learned again. Yeah, will be used again in chapter 7 when we learn about the electrostatic field after this. Yeah. Okay, so this Tuesday we're going to proceed with chapter 6, which is on the uniqueness theorem and also Laplace and Poisson's equation.